Yeah. Good morning, everyone. We are going to begin. So first we have the welcome on the speech.
Welcome, welcome.
All right, so right now I'm trying to introduce Lee, but Lee, your phone has to go. Okay. Okay, excellent. So I'm happy to introduce our first keynote speaker for the very first COI Combinatorics Lectures. I'm hoping that this grows and continues, and we're going to just have lots of fun as we get early on. So I'm happy to introduce Dr. Lei Xue. So she received her PhD under the direction of Isabella Novick at University of Washington, and that was actually recently, last year, 2022. She's an up-and-coming mathematician. She currently holds a postdoc at the University of Michigan, and her interests are in algebraic and geometric combinatorics, especially the combinatorics of polytopes, cosets, and CW complexes. So today she's actually been speaking about her interests and a group of Grünbaum's low bank conjecture with geometric polytopes. Thank you very much. Let's welcome Lee.
Thank you, Margaret, and all for having me here into the world mechanism or complexes. Yeah, I'm very happy to be here. So today, how to do this? Today, I'm indeed going to talk about a lower bound conjecture made by Grünbaum on base numbers of general numbers. So we'll start with introducing you to the conjecture, then we're to go over the proof of the conjecture, and then we'll try to generalize it, trying to generalize this conjecture in a broader setting, and this is one of the I strongly recommend this. Let's start from the very beginning. Let's define the polytope. A polytope is nothing but a complex called of finite set or D. And in addition, you ask for that finite set to be affine independent. You got polytope that's called simplex. On the right, which is simplex. Move on. Now we different bases. If we intersect the polytope with a hyperconnecting space, such that the intersection is only, so it touches the polytope, but no intersection in the interior, the intersection is called a phase. So here I have a phase, which is dependent on. There's another phase on that blue simplex. So that's dependent on its only touching at points. That point is a phase. A k-dimensional phase is called a k-phase for short. And depending on what that k is, we'll give them different names. So zero-dimensional phase is those points are vertices, one-dimensional ones factors. And for a d-dimensional phase, we always say it has a unique d phase, which is different itself. The d minus one dimensional phases are the maximal properties of the polytope capacitance. Okay. And finally, there's the vector. We call that the phase vector or F vector for short. That keeps records of all number of phases in each direction. And as k, we just denote the number of k phases of this polytope. Here's the F vector of the previous of this green polytope song on pathways. It has 10 vertices, 15 edges, and if you count 7 true phases. Now we ask this question. So what about this? Is it an F vector of some polytope? This is a very difficult question. And in my opinion, or in many people's opinion, it's the center in the area of study for phase vectors. So what integral vectors are F vectors? Before we move on, let's first zoom in. So instead of looking at output, we can just look at some family of polytopes or simplicial ones. The simplicial polytopes are those whose facet charges, for example, all two faces need to be triangles, and so all faces are simplices, and here are some examples and non-examples on the right. Okay, so I can only do option 3D. On the right, you can see that each of those polygons at least into something that's not a triangle. Okay. So in this family of simplicial polytopes, we actually know the story pretty well. First of all, there's a theorem called lower bound theorem by Matroids and Matroids in 1703 and 87. They showed that a certain type of polytope called stacked polytopes have component-wise minimum factor. Means their F factor is the minimum, is minimal in every entry. Okay, we know. We also know the other side of the picture. The upper bound theorem was done by McLuhan in 1917. And it showed that another family of polytopes called cyclic polytopes will have component-wise maximum factors. And finally, there's G theorem proven by Villar and Lee and Stanley in 1980, and they gave a full characterization of all F factors of simplicial polytopes. So given the integral vector, just like the random one I gave you before, G theorem will be able to tell you if there is a simplicial polytope with this F factor. Okay. One thing I want to mention is that so all these results were proven for simplicial polytopes. The upper bound theorem actually generalizes to all general polytopes for the simple reason that if you start with a general polytope, you can always perturb the vertices, so it becomes simplicial, and that only increase number of cases. The upper bound theorem is small, but not the other big theories. Here's the station now. So in that subset of the polytope, simplicial polytope, we know almost everything in the area of F vectors. We know very little for polytopes in general. That should show others. And as an example, there was a conjecture by Brown. I think he made it around 1995. Someone told us 1991. And it's a very simple conjecture, which is saying that if you have a polytope, the number of K faces should be at least bigger than or small or greater equal to the minimum of the number of vertices and the number of facets. If you see some polytopes, you believe this has to be true, but it was only recently proved by junction. Okay, so maybe the full preposition is still very hard. Let's go back to the lower one. And explicitly the problem is the following. Given total, if you fix the dimension to b and the number, you see the person, okay, that's it. Yeah, if you fix the dimension to b and the number of vertices to n, you can ask what's the minimal number I can choose. Okay. And moreover, you can ask, similar to the case for simplicial polytopes, is it possible there's one polytope whose active factor is componentized? Okay. And in general, we don't have a conjecture. Well, we don't have a bound on the number of vertices. We only have a conjecture when this n number of vertices is at most 2 times dimension, and the conjecture was given by Grünbaum, and it was in his book, Convex Polytope, the yellow cover one from 1967. And explicitly, here's the conjecture. So here, dimension is the number of vertices is up to 2b, so we say there are d plus s number of vertices. And then Grünbaum conjectured that number of k-faces of such a polytope is at least this alternating sum of binomial coefficients. Now, this might look mysterious. What this formula means will be there in 10 minutes. We'll be working with this formula, so let's give it a name. This is also the notation in Grünbaum's book. B sub k, and then in the parentheses, the first entry denotes the number of vertices, the second one denotes. That's probably the most famous picture of Grünbaum. He actually worked at Grünbaum and didn't know that was yeah, so I kind of. Okay, so the tracer dots. Grünbaum himself showed that this conjecture is true, this formula is true when x is 2 real. And what is x? It comes from this d plus 6 number of vertices. So essentially, that's the case when a polytope has d plus 2, d plus 3, d plus 4 number of vertices. If d is rather small, this covers a lot of cases. When d is big, this is not so big. And the only other result that we knew was from a paper from 2015 by Nada Willem and Sensual Grünbaum and Yost. And they were able to show that the conjecture is true when k is 1. In case over here, so they were focusing on the number of matches. And in the paper, they used a lot of methods from graph theory, a lot of case studies. Yeah, so they were able to show that this is true for the number. And what I was able to show in my first paper, well, in the paper in 2020, was that the conjecture is true, and it's completely true. It's true for all dimension d, for all s up to d, and it's true for all k. Now we're going to go over the proof today. Any questions so far? Okay, so one key ingredient in the proof is what I call the Q proposition. It's this proposition here on the board. So if you try to think of this problem, you want to prove a lower bound for polytopes. One way you can think of it is that you can try to find relations, right? Relations among vertices, relations between vertices and facets. This proposition sort of does the opposite. You can see that error in the statement. So here we don't have any restriction, for example, on the number of vertices. We just have any d-dimensional polytope. And we pick a random set of n number of vertices. So simply they shouldn't have among us. But the key proposition says that a number of k-faces that contain at least one vertex in this set that we chose is greater equal to the summation of finite. Right. And to show that, we use vertex figure. So given the polytope and one of its vertex, you can define a vertex figure very simply by doing the following. You slide in the pigment that separate that vertex from the rest of the polytope, and you just look at the intersection with that. The intersection, if you start with the default of the intersection will always be a D minus one dimensional polytope, denoted by B. And you always have this max property. There's a max projection between on the left, the set of all three-dimensional spaces that can contain this vertex B and the set of all mixed spaces in the vertex figure. And that projection is very natural. Right, and take the face, for example, take this edge that contains B, you just look at the intersection with the height of these two. Despite the intersection is, for example, that vertex. And of course, this triangle becomes an edge in the vertex here. So here are the face lattices of P and P. So you can see in the clear that really the face lattice of P B is the upper interval from B to that top elements in order to make face lattice. Okay. So to prove this key proposition, what we do is that. Okay, so let's start counting straightforward. We want to count the number of K faces that can sound A's. Let's start counting. V1 is a here. I want to count all K faces in P that contains V1. So that's equivalent to counting the number of K minus spaces in this K vertex. Right? And then to V2, I cannot compute the vertex figure of P at V2 because then I'll probably be overcounting. Instead, I'll find the passive I call it F2, pairing with V2, and I count the number of pieces in this vertex. So as I keep going down, I'll find a sequence of faces F1, F2 through Fn. So that each Fi contains the I and not anything. And these are all. So all of these are placeholders of polytopes. So they should at least contain the number of K faces in a sequence because the simplex is the sort of the minimal polytope. Yeah, so that's quite straightforward once you come up with that sequence. And then we can prove the conjecture, and of course, it's going to be an induction. So the base case for the first 7 cases with them, all you need to show is that suppose the same holds for all S prime and D prime should hold for DNS. And really, what we do is that we first take a facet that's good for induction. So we need to have at least 2 vertices outside it. And we label the vertices that do not make it to add V1 and Vn. And then we can start counting immediately. So we want to count this number of K faces. If your K faces of P, either you are K faces F, or you should contain some outside vertices. Right? And if you're in this first case, you use the inductive hypothesis. And if we're in the second case, okay, so the inductive hypothesis is sort of counting numbers in this shaded area. And then if you contain some outside vertices, use the key position. So we're kind of swiping this bit like this in this way. And the following goes, okay, so the red part comes from the inductive hypothesis, the blue part position, and of course there's some rearrangement that you should do to make it look like a one like they do, but really there's no. So I don't have a full detail here, but really those are corollaries come from Pascal's identity. So yeah, this at the end, we get one after K of B is we're going to bound. If and of course, this is one special case we deal with when you cannot find a facet with two vertices, at least two vertices outside of it from the beginning. But then it means that, okay, for every facet, there's one vertex outside of this, so the entire whole is a cone, and that's true for every facet. So he has to. Okay, by the way, I should mention that the conjecture, the following conjecture, if you test, like when axis is one, it should be this. Okay, so we're done with the proof of the conjecture. Any questions in time? Any questions? Okay, so next we're moving to the treatment of equality. And by that I mean answering this question. So which will pass this act? And we can also ask, okay, are there some polytopes that may be satisfied this equation for some case, but depending on our case? And that comes, okay, so then I can tell you where that one, like how did it do? So Grünbaum had a candidate when he was looking at this. That formula comes from an affect of something, and we're going to do that construction, right? So first, let's define what it means by saying that a point in the space RD is beyond S. It just means that when you take the splitting vector plan of that passive graph, it should have the entire photo on one side and that point floating right side. Okay. And once this is defined, given a photo and some point in the space, we can count how many facets this photo is that beyond. So here, this acts beyond one facet because the supporting it's beyond exactly this one. But if you move it a little bit, right? So now it's about 2 facets. The other way to think of this is that pretending that you are at a point X, how many facets can you see from this? Okay, so now, we also need to normalize the photo again. Given the photo, there's always a photo. Space length is like upside down. So the photo is always also d-dimensional, those are d-dimensional, and the facet is corresponding to the vertex of axis. One example is right, for example, this point, this vertex of this purple photo is contained in 4 edges. And that's probably because it's corresponding to one of the rectangular facets in this green one, which contains 4 edges. Okay, so let's do the conjunction by so we start with a simplex with dimension A, denoted by T superscript A. And we want to add a new vertex to this simplex, and where do we add? We put a new vertex beyond exactly n facets of this simplex, and that will give us this TA sub n. Photo, it's still simplification if you think of it, and it's still of the same dimension. Now we can make these 2 vertices. And then you just apply a multiple pyramid over this simplification photo. That will increase the dimension from A to D. We do D minus A pyramid. But I'm going to do that, it's probably no longer simplification, not simple. But it still has the equals 2 vertices. Right below here, I can start with a triangle, which is 2 simplex. If I want to add one new vertex beyond one facet, I can pick here, and then I can come over it to get T3, 1. So now this is probably not the best notation, but it has some variance, so we're doing it. Yeah. Okay, so equivalently, in more modern language, I would say, the first step is nothing but the direct sum between two smaller dimensional simplices. And the second step is just finding a new sequence for the direct sum. Okay. What's nice about this construction is that actually after the first step, we get every sequential default of the previous two verses. And after the second step, we actually get every default sequential no, every general with equals to verses. So this is gives the whole family of polytopes with two more vertices. Okay. There are two elements of condition. So first of all, let's try to do this. Start from this 3 simplex, and if I want to get T3 sub 1, I can add this one over here because this stuff is going. You can see. Get that one. If you want to get T3 sub 2, then maybe you want to add this brown point because you can see both this stuff that comes. Look at that. And then you now you can take your hair to see that they're actually the same. And that's always true. Adding a new class, adding a new vertex beyond M process is the same as adding it beyond D. Okay. So this actually gives you exactly how many D sequential components, D sequential polytopes will exactly do this. Right. That's roughly equal to the pair of this application. This gives you areas. And so those operations we just see, it's easy to believe that, right? It should be very easy to keep track of the app, right? And this is the explicit problem. So we know this family very, we know this. And in particular, if you plug in the correct A and M, so if you let A equals X and M equals 1, and you dualize this polytope, this gives you exactly the F-factoring movements. So this polytope was what Grünbaum had in mind, and since we have proved Grünbaum's conjecture, we found this, we show that this indeed has the component-wise minimum. And here just the two examples. I already have those pictures in the previous slide. Okay. What about the second question? Like, are there any other minimizers? Any other minimizers for some components, not for everyone? Then we go all the way back to proof of key proposition, the main theorem, and watch C. Under what in what conditions will all those equalities be equalities? Okay. And remember the place limits slightly roughly that place that is a P particularly several parts. When will that always guarantee us that we actually not miss any that place limits, right? And so there are many programs you can get from the code when they follow the code. And the most important thing is that we will show that we show if this equality is true for any k between 1 and 2 minus 2, then this p needs to have exactly those two facets. And we're essentially done once we show this because we know this family very well. Because if you do this, it's a polytope with equals 2 vertices, and I have so it turns out that minimizing the polytope that Grünbaum was considering was the unique minimizer. Okay. So theorem says if the lower bound is full for some k between 1 and minus 2, then there's something off. And in the case when k is 2 minus 1, so really you're in this case, this is special because in this case you're only fixing the number of vertices to n and the number of facets to d plus 2. In that case, probably more than one boundaries, boundaries equals to, well, probably more than one equals to from that boundary. So as long as you can find to be a access by these inequalities and equalities. So now that Grünbaum's conjecture is proved, and the proof, as we just saw, was natural and simple, very innocent. We're thinking if there's any possibility to generalize. One direction is to see if the conjecture actually holds in a more general setting. So this is the more general setting. So we define diamond lattice as a lattice such that every rank 2 interval is a dimension. Okay, so every rank 2 interval is exactly 4. Okay. Remember this picture actually, right? It seems that we can do the argument by just looking at the faces. And it's true because one important property that we was taught is that we call that facet distinguishability. So facets are able to distinguish different vertices. It means that given any 2 vertices, you can always find the facets, find one facet at least that includes one or the other. The same is true for diamonds. So the coatoms of diamond lattices are also able to distinguish different atoms. So therefore, we can push the proof of the Grünbaum's vector to post-set languages, well, translate to post-set language. And therefore, we're going to show that actually the lower holds with all diamonds. So there we're going to the number of with relative pairs. Well, for the equality cases, it's much it's not that simple to check if that okay it's much harder to check if the minimizer is unique in the setting of all diamond lattices because there's just too many of them. What we can do is to find somewhere in the middle. So the lattices of strongly regular spheres are all diamond lattices. And what are those spheres? So regular just means that the attachment map, if you have a CW complex, are all being used. And to say it's strongly regular, which just means that in addition, there's a intersection property. We need the intersection of the 2 cosine in also set. It can be the end, but it cannot be more than so. These are nice, and one thing that's particularly nice about them is the theorem by the Schmitz, which shows that if you have strongly regular spheres and the number of vertices that 50 + 2, then it has to be a polytope. So this gives us the theorem for free. Says that the theorem for the equality case actually holds for all strongly regular spheres. So now we have those strongly regular spheres with B plus S vertices, and the lower bound actually holds for some k, then that polytope bound is still going to be. Another direction will be the following. So Grünbaum's conjecture is up to n equals to b. We know that we don't have conjecture when n is bigger. Will we do better, or why is there no conjecture? So if you take your mouse omnibus and you try to not even fit, just work on the one, it still holds if you copy n equals 2 equals 1, for example, then it should be very clear very quickly that's the real lower bound. It doesn't hold when n is greater than 2b. But we can still try to find out, like we should try to hook up new conjectures, new guesses for the lower bound for the Muslim case. But unfortunately, at least when n equals 2b plus 1, in some cases, the component-wise minimum conjecture just will not exist. And here are two photos that we're looking at in the 2b plus 1 case. Let's start with P. Okay, so you can see that most of them contain some code that we constructed. This one is here, and this is here. For P1, we start with, for example, in the 3 case, this 3 poles of which 5 vertices, we stack over a simplex acid, and you do this. This is the same as, in this case, it's the same as finding a simple edge and discounting from that edge. And this photo was also constructed in the same paper from 2019 by essential languages. Yeah. And they call this from this picture, you can see why. And P2 is the dual of some member in that group. But one thing to notice for P2 is that you can see that it only exists when D is equal. With those two photos, what it showed in the 2019 paper, never launched the organization of yours, they showed that when D is greater than 5, P1 actually is unique minimum for the number of atoms. Okay. But remember, because you stack over this photo before you draw lines, P1 actually has one more capacity. So those two strictly inequalities right there show that at least when P is even, there cannot be the component-wise. Okay, in this case. But we can still see. In fact, I was able to show that for P, a strongly reconciled sphere with greater or equal to 2b plus 1 vertices. Okay, so there's about a number of vertices. It would also have some restriction on the number of facets. Okay, so if we break this problem into 2 parts, if you restrict the number of facets to exactly P plus 2, the minimum possible, then the poles of P2 will give you the number for all. If you allow the number of facets to be greater or equal to P plus 3, then P1. And right, those 2 poles, you can compute the aperture very easily, very explicit formulas. You can compare them. You can compare them, and then you see that roughly the aperture of P1 will be smaller in the first of the aperture, and P2 will be lower. And also, I will mention that in the newer paper, same example of other the essential rules, they also show similar results. But they show that P is a polytope and after 0 equals 2b plus 1, then either P2 should be. I think my theorem is gives you exactly which polytope is about, and it's this is slightly more set. Whenever I say strongly reconciled spheres, in the actual paper, actually the strongest version we can show that this experience for some normal civil benefits with nice distances.
Super results. The first time I went to a talk with some people clapped. Ooh, that's so nice. Any questions for Lei? Yes. Aaron.
Does it say anything in the H vector world?
Very good question. Okay, so if you have the middle vector, you do have the middle H. Well, the componentized thing. But on a similar topic, I was also curious about, for example, the flag vectors or even the toric H vectors, city index vectors. I didn't go too far into the flag world, but I did check the toric H vectors. The minimizer, when n is up to 50, indeed give you the minimal toric H. It's very easy to see because the constructions are very easy. In the 2D+1 case, there are two candidates, right? One of them has the minimum for H vector, the other one is not. I'm not sure what that will invite us to.
Any other questions?
I have another one.
Great.
Is there any way, so you're talking about like making smart choices of vertices and facets. Is there any way of like translating that into some operation challenge?
That's reasonable. This is sort of reminds you of Stelling's this.
Yeah.
At the beginning. So
It's
definitely geometry like that.
No, I cannot give an easy answer, but it's very possible.
And you said you were looking at CD index properties, or I mean, that's like a whole different writing, because you're removing all these relations, so you don't know.
Yeah, I can't think of it since I've been here. I should be able to do something that's not, but they're not.
Thank you for saying that. It's fun. Any other questions? Okay, if not, let's thank Lei again. So we're probably a little bit early, which is fine. That's good. It's a good chance to chat. Coffee should be arriving by never fear. I think that's okay. It's good. I know. Right.
Yeah, I mean.
Do you have to do it? Yeah. Do you
Hello,
Yeah, I know.
so when we do the second class, we have Eric Katz from Ohio State and Eric received his PhD from Stanford under the direction of Ellisberg in Brunswick Hill. We have other positions that do in the optic, and then was the first of the right. Eric was a faculty member at the University of from 2011 to 2016, and then he moved to Ohio State. You were under yeah, we're under Ohio State. He's currently an associate professor of mathematics. And he currently holds an NSF career grant, and it was named in use of field medal long citation as a discoverer of combinatorial analog of Hodge theory. And Eric described himself as an algebraic geometer, that's combinatorics, number theory. And in college, he was a radio DJ at OCSU Stanford and WXU Durham. So take it away.
Thank the organizers for inviting me. It was actually granted the postdoc already meeting. Probably the last 2 weeks spending stuff better than postdoc. All right, so what we're going to talk about here is models of matrix. And I'll define matrix. I'll define matrix 4 times in this talk. The idea is that matrix is abstracting your subspaces, and there's certain geometric construction to a linear subspace, and that spits out some algebraic structure which is posed upon the course, and hopefully have some positivity properties, which is how you what conjecture the nature of it all. But what I want to concentrate is what are the combinatorial analogs of certain geometric constructions that occur in this world. So not every matrix comes from a linear subspace, that's asymptotically 0% do. So what can you do that's like geometry? And I'm going to give you multiple answers. And the goal is to understand unit invariance. I'll explain unit invariance if we're interested in, but we may not be able to get to like how we relate to this. Okay, so let's start with matrix as notorious into subspace. All right, if you don't know what a matroid is, that's fine. I wasn't to look up a definition later. So the idea is start with R plus 1 dimensional subspace of an n plus 1 dimensional vector space over some field. And here, coordinates are going to be important. Related coordinates x naught through x n. And I'm going to suppose this V is not contained in any coordinate subspace. So find coordinate hyperplanes be the lowest point where the coordinates is 0. And so I think the coordinates 0 through n. So we use brackets n to denote the second. And I'm going to look at the intersection of these subspaces with the coordinate subspaces of the vector space V. So subset of an indexing set, we define HI to be the intersection of the relative coordinate subspace. And the idea is that matroid is oracle that just remembers the dimension of those intersections. And so I've got my subspace, I have a coordinate subspace, and I look at what dimension subspace it has. So, okay, I'm just going to try to remember a row. I'm going to put axioms, conditions on row that have some fighting chance that can come subspace. Okay, so what would be some good conditions on the row? Well, if I intersect all the coordinate subspaces, or all the coordinate hyperplanes, I should get the origin, which should be coordinate R plus 1 V. Second, if I intersect more coordinate hyperplanes, it should cut out, it should cut out a smaller dimension subspace, so. Putting more efficiency increases the codimension. And it really only increases the codimension by one, every time you do it. You have this condition. And then you should have something completely non-obvious. So, and for range functions, this row is called a range function that non-obvious needs to be called subline. There's a million definitions of matroids, and they usually have the form of something obvious, something obvious, something obvious, something weird. Okay, so what is the weird thing? What it's saying is the translation of a property of substance. Okay, so imagine this as the intersection of V intersect HI with V intersect with J. All right, well, what do you expect in the intersection of each? Well, it's the sum of these dimensions minus the dimension of what they span. So if things were coming with transverse, this would be an equality. So this is just additivity of codimension under intersection. So these are the four properties. But these four properties do not characterize linear subspaces. I wanted to study objects that are just these range functions. We take subset of the indexing set to non-negative integers. Satisfying these axes, it's put me in the world of matrix. And asymptotically, 0% of matroids come from linear subspaces. Now, if you try to read a book about matroid theory, there'll be like 7 or 8 definitions of matroids. And this is called cryptomorphism, that they're cryptically connected or in connection between these different definitions. And I can never remember any of them. So I'll give you one more, which is the characterization by bases. So the matroid is a non-empty collection B of subset of integers from 0 to n. One of my undergrads in foundation math class on the power set. It's like that. Well, I have that simplification condition. I have 2 bases, B1 and B2. And I know in I that's in B1, but not B2. There's this J and B2, not B1. So that B1 minus I union J is a basis. Okay, so what are bases? So given a range function, you can define a set of bases to be the set of R plus 1 element sets of range R plus 1. So what is this? This means the collection of R plus 1 ordered hyperplanes that intersect out to the origin. So it's the linear independent way of cutting down to the origin. And what is this basis? It's called the basis exchange axiom. And it's what it says is by 2 bases, I can walk from basis 1 to basis 2 by introducing a new element and taking away an old. So the idea would be if I have some I, it's in B1 but not B2, if I do is I can imagine if I add I to B2, there would be some linear dependency relation that would let me And it would have to involve the I that I added V2, and the J is some vector that occurs in the linear dependency relations. I can write this vector occurs in this J, and I get a new basis, and I want this is the combinatorial abstraction of being a basis. That's one definition of matroid. I'm going to give you one more, which is a different, it's very close to the definition in terms of range function. So the other definition is you have a collection of flats. And I'm not going to tell you the axioms, but it's the set of subset, my n element set, my n plus one element set, that conveys the all right, let me try to explain what this means. So you've got this linear subspace, you have the coordinates type of parts, and that gives you subspace of that half. And you want to just remember those subspaces. You don't remember, you want to remember what you intersect to get there. So what you do is you index those subspaces by the maximal set that cuts them in, maximal set of coordinate things happen. Are we okay? And let me just give you one example of matroids, and then I'm going to start going to geometry and then go to combinatorics. So one example is going to be uniform matroid. So this is a red R plus one matroid n plus one element set, where it would correspond to the most generic choice in R plus one dimensional linear subspace. So that means that if I intersect with an HI, if I is too big, it should cut down that coordinate number of elements off. So I guess picture you should have in mind is something like this. If I intersect with one element, here is my subspace. This is the linear subspace, but imagine it's curves of characterization. If I intersect this guy, by one dimension. If I intersect this down by one dimension, I intersect this axis down by one dimension. Anyway, that's a picture you should have in mind. And here the bases, well, any R plus one element set should cut down to the order. The set of bases is all R plus one element subset of my ground set. In the class, well, I can intersect these coordinate subspaces. If I intersect with less than or equal to R, then that gives me something. And you can check what it is based on the coordinates are 0. But then if I intersect with R plus one coordinate subspace, it cuts down to the origin. And the maximum set cutting down to the origin is all right. All right, everyone okay? So I'm about to talk about the unit invariance that we might be interested in. Okay, so the first one I'm going to talk about is the characteristic polynomial, which I learned about Matroids like 12 years ago, 12, 13 years ago. So characteristic polynomial is a generalization to chromatic polynomial for graphs, but I think about it as an expression. So what I want to do is I'm going to look at, start with my coordinate my subspace B, and I'll look at all points with no zero coordinates. So I'm taking B and I'm removing all the coordinates. And I want to count the points in here exactly once. So what I do is I remove all the hyperplanes that intersect B, and the coefficient here is all 1. But then there's points of intersection of those, so I have to move too much. So we have to add stuff back in. But then I added too much stuff back in, so I'm going to take stuff away, and so on, which is for so just inclusion and exclusion. And then what I do is to every linear subspace, I give it an inverse dimension. So if there's a subspace W, I take Q to the next dimension. So the characteristic polynomial ends up becoming, well, this is R plus 1 dimensional. And so on. Zero dimensional. All right, in some sense, the characteristic polynomial is an evaluation of the motive attached to the intersect A star and n plus 1. That doesn't really mean anything, it just means there's sides. But I like saying the word motive in combinatorics talks. Are we okay? All right, so
Do you want to do this example?
oh gosh, I'll get it.
Or two, you're taking the measure of the space lines.
Yeah. Oh. Okay, and that this picture of this perfect. I think, yeah, so let's see. We take. Yeah, so let's do. Never trust myself, so. Okay. So if we have something that's two-dimensional in 3D space, let's be generic. Generic as possible. So it can be I know the answer is going to be truncation of rays, right? Three-dimensional space. Using brackets too. Okay, so these are lines that I remove, and then I remove too much, but I have to add some things back in. So if you think about the intersection of H0 and H1, that's a point. So let's see, it was here, then I removed it twice, so I have to add it back in once. We did it for all the other ones. Okay, so that's the most basic expression for the intersection. K star Q. And then I just remember the dimension, so I get Q minus 3 squared Am I losing my
You don't have to
notes?
subtract all the intersect H.
Oh, yeah, the word, yes. So,
I mean, this is what you do more than reference.
yeah, it's because I,
They don't have to say that.
yeah. It's because I think about these in terms of a growth neighboring motives.
I know, you're losing those.
Yeah, I'm trying to be nice, Okay. I didn't know there would be the exam today.
I'm sorry.
No, it's okay. I found myself on a virtual exam.
You know, the coefficients, by the way. you have to know.
Yeah, it's amazing, like, look at the coefficient ball. They alternated sign, and moreover, they appear to be log contained. Not that. Okay. Yeah, you this was amazing. So. This used to be wrote as conjecture, used to be wrote up here. The characteristic polynomial is log contained. And internally 0 to. So what does log contained mean? Means you take a log of the coefficients, the log of the absolute value of the coefficient, it forms a concave sequence or regular multiplicatively like this. Okay. And it suffices to show the reduced character. What's the reduced characteristic polynomial? Turns out 1 is always the root of the characteristic polynomial. So let's just divide by 2 minus 1. And so mu superscripts are the coefficients of the reduced characteristic polynomial. All right, that's one thing I might want to count. Another thing, and this turns out to be considerably is the count class. So let LK be a set of rank K class. And then it's a theorem of Graydon Mather Proud and Long, which it says it's called compound vector. Which says that you have the following equality. So I have some K and some J that if you imagine these cement situated from 0 to R plus 1 with the raised to the class. So I've got some K class, I would K from the bottom, K from the top, and then J in between, and there's more class there. And this is very difficult. Like, so you're quite a bit of this, it's really hard to get at the number of flats. Like there is a geometric way of getting at them, but like you have to use quite sophisticated algebraic or topological techniques to do the realizable. And then the common fraud is quite difficult. The word being intersection form. All right, and then I'm not going to tell you what the result is, but there's a lot of happy properties of the compound memory. These are the Washington Cabinet results are recent to the Erget or Spain and the second. And it involves something called the variable Matroid is universal variable practice. And I think of it as deeply weird. So here I'm summing over subset of the ground set, and I'm remembering the code of the set, and also thinking about the number of elements, the number of units among the elements in that set. And the more I think about it, the weirder I think the top polynomial is, because it remembers this number of elements in a class. Like something like a characteristic polynomial is really post-second. Like you just remember the last class. This remembers the size of the class. I find that very strange. A lot of the constructions I'll talk about aren't really sensitive to the size of the class. Okay. So questions, concerns. Now we're going to get into the main body of the talk. So let's talk about the bottom of the page. So I'm going to talk about like you run event program, hoping it's an algebra, but along the way some combinatorial object concepts. All right, so the first one, this is historically the first one. First started things studying in the late 80s, early 90s. And then it moved for the polytopes. Or at least was studied by young in the 90s. Jack Edmonds started studying Matroid polytopes in the 60s. And has anyone ever tried reading any Jack Edmonds stuff?
Yes.
It is crazy hard. Like he is so much smarter than you when you're reading him, and he's not afraid of letting it be known. Kind of a crazy dude. This is White Cast's house every day, and he had the peanut and meat conjecture written on a rock, engraved on a rock in his yard. Okay, so the idea is to erase this. I'm going to attach a problem. I'm just going to start on standard coordinate vectors. Corresponding elements in the basis. And then the matrix polytope is the convex hull of those points. And these tend to be pretty hard to draw. So the only one that anyone ever draws is U2-4. It's like, yeah, they draw your own polygons, they're silly, and then good luck finding for E or I. So I'm just going to draw U2-4. That's all of okay, I'll try to this is in 4-dimensional space, but every basis has the same size. So that reduces the dimension of the matrix or the unity dimension from 4 to 3. It lies in the hyperplane where all the coordinates end up at the rhythm. So in this just turns out to be And that's not regular argument. And where does this come from? It actually does come from geometry. So by a linear subspace, we view it as a point to the Graph common by parameterizing certain dimensional subspaces of some ambient space. So there's a point in the Graph common corresponding to this point. And then I've got an action based on the input. It's a non-zero coordinates in K. So we're looking at all points with no coordinate 0. Then I have to act on this point by diagonal. So it's doing, you've got an linear subspace, you rescale the coordinates to the ambient space, then it traces out a whole collection of subspaces. That and those are either the data of mutual polytope. And in general, Matroid polytope has a uniform Matroid is on paper simplex. But it's a simplex convex hull of the standard unit basis vectors. So here, convex hull of the subs standard unit basis vectors and their subs. All right. Is everyone okay? All right. The second model of Matroids are urban variants. But then I need to make an aside. We need to talk about the permutation override. Okay, so you notice my index early, my dimension counting early one, and very R plus 1, and N plus 1 is dimension. The reason why I was looking at okay, so I now have an higher dimensional projected subspace. And what I want to do is find an algebraic variety capturing the combinatorics of the Matroid. And I'm going to do things to this ambient PA. Okay, so projective space, it has coordinates at the point where all of one coordinate is 0. Okay, there's n plus 1 points. I've got the line. I have the planes containing 3 of them. It's all the same thing as intersecting coordinate subspaces. Or coordinate hyperplane. And now I'm going to do, I'm going to apply the operation blow up to the ambient projective space. So what that means is I look at each of these points, I remove them and I replace them with something codimensional. So I replace them with n minus 1 dimensional variety. Then I look at the lines between pairs of points. I remove those and I replace them by something codimension 1. And I keep doing that. There's a way of writing down what I'm doing by coordinates. So there's an analog dealing with the space you get in terms of something like homogeneous coordinates. But it's not like so then we all points subspaces and we get an algebraic variety called the community coordinate. And So. So here is the set of no coordinate equals 0. Here is my projected space. And then here's a permitted equal variety. There's a projection there. And for those of you who know about promoter maps, this is how is the complementary one. It is something very classical. You just take a typical and this is defined everywhere by action information, but it turns out that you can define it not to be equal. All right. Okay, so now okay, now I haven't done any capability of subspace. So what I'm going to do is take what's called a proper frame. Good. Do is to look at the points in the projectization. You know, coordinates equals to 0. I look at its image in the permitted 0 part of me, and then I close it. And okay, so I told you on the loading stop. And so what's happening, what this does, this proper transform, is it lets the projected subspace go along for the rock. So I look at the points, I look at the subrise of this side that arise from intersecting coordinate subspaces. And what I do is I blow them, I replace them things of codimension 1. All right, it sounds fancy when I say blow up. Here, let me just give you some files. Remember, you're teaching Calc 3. And you ask your students to take the limit of some function in the plane and compose on a line. And the function isn't defined there. It's something like y over x. So what the blow up is just you remember y in the case of the plane. And so remember is when you approach your subspace, how you approach. Okay, so the upshot thing on this object is called the wonderful specification defined by Puccini and Perchisi. But the cool thing is, or it is cool thing. This is the cool thing. But the application for getting part here is the one that we did in Hahn itself, which is the coefficients of the reduced characteristic polynomial is an intersection of Alright, so what does that mean? Well, what it means is I take, or I'll tell you what I'm saying. You take a bunch of subspaces here, or a bunch of hyperplanes here, a bunch of hyperplanes here. You look at the inverse image of equal. You intersect and the one application. And you count the number of points of intersection that turns out to be the coefficient of the reduced characteristic polynomial. So it's a different geometric formula for the coefficients of the characteristic polynomial. And it's a positive formula. But the cool thing is it arises from intersecting subvarieties here that have positivity properties. So they're what's called NEF. And NEF is an algebraic geometric analog of convexity. And you get law of cavity by applying virtual density cascading law. And really, it's just a common, where it's now great geometric analog of Alexander eventually equality in polytope theory. Okay, so it gets worse.
We need a 15-second break.
Sure. You got it. You need to. Hey Siri, set a timer for 5 seconds. All right, cool. All right, so what if M is not like this? All right, so now I said this is intersection theory. And really, intersection theory can be viewed as taking the product of whole knowledge. So what I would like is combinatorial stand-in for the cohomology we want to compare. I really only care about the even bits. And because I'm an algebraic geometer, I'm using algorithm. Just think about it as cohomology. Just think even it's really the same thing as even cohomology in this case. So I'm going to do some algebra. I'm going to start with algebra, and then I'll go back to like geometric combinatorics. So just bear with me. Okay, so all right, so I have local points and local lines and so on. So what I'm going to do is I'm going to look at read generated by the world's of plants. So let's just pretend like I'm doing this for you and one time. Then one application is just for me to equal to work. Okay, so generated by this guy, these guys associated with the flats, and they pose two conditions, which is that these guys could not intersect if the flats are not. So what I'm saying is, if the linear subspaces didn't intersect to begin with, then their divisors should definitely not intersect. And then the other thing I want to do is fortify linear relation. Okay, so and this will indeed give me the cohomology of the torque. I just looked at the algebra generated by these guys subject to this non-intersection, non-comparability equation, and some linear relation. And linear relation is all J round set. Some of the stuff that can be I. Subset of J. And really what it's coming from is what's the cohomology of this guy? Projective space. Well, it's going to be generated by hyperplanes, and every hyperplane should be the same, represent the same class. And this is just going to encoding that in this new world. All right. Now I got this gives me the cohomology of the integral torque property, but then do a little application associated with Matroid. What I do is I just portion by these generators that are not flats. And alternatively, written in the papers, it is the following. We have all, these are all the properties of the trivial class, and here are the incomparability and the narrow relations. And with a ton of hard work, you prove advanced cascade in this set. And this is the Hodge theory and combinatorics setting. So this is where the Hodge theory, the Hodge Riemann relations, all this mess comes in. And it's proven by it's originally proven by a very complicated inductive technique, but now are easier proofs. There's also this whole story related to Lorentzian polynomials. So there's now like a 10-page proof of Rhodes conjecture due to Brandon Lee. It's really cool. I don't really understand Lorentzian polynomials, but it's worth learning. I actually think this is an important development in combinatorics. So somehow, like if you write down the ax information in terms of class, it's a certain interlacing property. Which lets you travel, you go up, down for searching through flats. And somehow that's what's strong enough to give you log and cap. I think there's money to be made by studying similar properties and counterproducts of that property. You can understand what your pocket's going to do. Like I think it's hidden in there, but he says it's not. I don't understand the relation, but like somebody should study that stuff. But I digress. Okay, so let me tell you one other question. I'm going to go back to the geometry. Like you could just write down the proof of the Rotarian conjecture purely in terms of algebra and geometry practice. But I want to do geometry and decide to give me another model. And in this story, I'm going to say it's going to be Matroids plus classes in the community of the picture is would be like topology, which is that well, a religious application includes the community of so in particular, there's an inclusion on homology, and this is the top dimension. So there's a fundamental class. Now, I want to look at that fundamental class inside of this. All right, and the cool thing is, I can define this class, or rather, it's planetary dual, even if the matroid is not represented, just in the data of the matrix. So what we're going to do is produce it's called a Bergman band. It's going to be, I'm going to write it in terms of homology. It's going to live in the challenge of the community will drive you at -R. That's the coefficient. And it's going to be defined by a probable object. All right, so let me tell you what that is. So So when we look at n plus one dimensional space, then portion by the all ones that all those points are ones. This is n-dimensional space, and this has the images of the standard basis vectors from this guy. We then to a subset S of the ground set, the associated vector, some of the BIs correspond to the elements that's, and then given a flag of subsets, we're going to look at the cone spanned by these vectors on these subsets. This is an S. When I teach honors students, they ask me this. Bah. The regular students, when I say S, they realize it's an S. Okay, so, and if I do this for all proper non-trivial subsets, this fits together. These cones fit together. So we're two-dimensional space, and we would have our base vectors E1, E2, or the image of E0 and the bullshit distance. And then corresponding to the flag E2, and here is E0, 2, here is E01, and now the cones again are all possible. So this is also called the greater arrangement. All right, now let's say you had U2, 3. So we have that corresponds to a generic line in 3 space, or a generic, generic line in projective 2 space, a generic plane in 3 space. And the first band associated with that is you just look at the cones spanning the flags of class. So instead of looking at all the possible subsets of X, as you do to get the integral band, I only look at the ones corresponding to flats in my matrix. And in this case, for a generic line, I will just say this. And according to law, you give a talk, you must draw this picture of the yields you're talking. So I have now doing my legal duty. All right, now whatever urban band you use, it has a property called balance. So what does balancing mean? It means if you look at something of codimension 1 here, and you look at the codes containing it, you hold on each of them with force 1, this would go anywhere on itself, the codimension. So there's a balance, like there's a zero tension condition, like in high school physics at the origin, use a particular picture, and there's a high dimensional condensation. And it turns out that studying objects that are like this gives you another characterization of things. So there's a theorem due to Alex Speed that says that you can characterize matroids as degree 1 probable cycloids. So a pure dimensional balance band supporting on the equal band is a Bergman band of H-core. if and only if it's a degree 1. And this is an intersection. The point is, if I have a linear subspace, it should intersect complementary dimensional linear subspace in 1. And this is a combinatorial coding of it, it gets a new definition. I got, do I have 5 minutes left or?
Yes.
Okay, so I'll say some words about another model of Matroids that was developed by Birgit Spackenstein. And I think this is really promising. That already beat the results. And one feature or approach, an approach that goes beyond this, is instead of just looking at a Matroid homology of the three-dimensional torque body, you look at it as a variable class. So what's happening is there's a torus, and by torus I mean just copy the star to the end, dilating that three-dimensional torque. It comes from the dilation of the empty space. And there's a gadget called the covariant homology, which is, it remembers more than just homology. It remembers something about group actions on things. And it turns out that you can lift the Bergman band from homology class to equivariant homologies. And this is pretty cool. And this is combinatorially conceptualized as piecewise polynomial functions. So there's a certain, you can attach a piecewise polynomial function on this guy to a matrix. And it's that time to tell you what it is. So it's a communicator band. The top dimensional components they're indexed by permutations. And given a permutation, this is the permutation that surrounds that. You can take 5 subsets. Oh, sorry. Like, explaining the common parts. Sorry, I'm going to talk about that later in a second. So, given a permutation here, you look at flag subsets, and then that corresponds to the and now how would I include the matrix function? So permutation, I'm going to consider what's called the less first basis of M with respect to W. So what is it? It's the basis of the following form. Where the increasing sequence. And I try to minimize. I imagine I've got the order on the ground set induced by W, and I try to keep the lexicographic minimal basis. And then once I have that, the equivariant lift of the Bergman band. It's These ones are polynomial function. Here, these TIs are the coordinates on Rn, and I just look at the elements that are not in the Lexford spaces. And somehow this gives me a piecewise polynomial on the Berkeley band. And if you run it through the localization machine, which spits out a fan, it spits out the Berkeley fan. And what I've been thinking about lately is using this guy. So the cool thing about this is once you get an equivariant with the cohomology class, you can compute intersection numbers for two equal equivariant localization. So that corresponds to a sum over cones. And so it's some sum over permutations. So there's some connection between these variance matrix permutation statistics. So I'm trying to understand that story. Anyway, but it turns out you can build a top polynomial by intersecting this class and some related classes equivariantly, and then that immediately that'll spit out some logical cavity properties, which are really cool.
Do we have any questions for the speaker?
How does the combinatorialist know about learning this alignment?
Oh God, you wouldn't believe how many times I get this question. It's usually phrased as you wrote matrix theory for algebraic geometry. Algebraic geometry is my algebraic geometry matrix theorists. I think some of it is in a pretty good state. So you have to learn, I guess the important thing is to learn the definitions of these cohomology classes. They all have combinatorial outcomes. So usual cohomology can be treated as there's Stanley Riser definition, which is really the matrix child, and then there's something called approximates. So you need to know what those are. Then you need piecewise polynomials, and you need to know the map of piecewise polynomials to the approximates. And to learn it in finite time. You just pretend like everything is cohomology. And you, I don't know, you meditate on a T box covariant localization of the moment polytope, or moment polytope and covariant localization from my favorite papers. So if you want to learn an covariant story, and I recommend reading that paper. Like it doesn't touch on the topology paper, but it's gorgeous. And I don't know, draw lots of pictures. Since I don't probably be in this research area, it's like running the pictures and doing some examples.
Any other questions? This thing speaker. Theory announcements, I get to go to lunch now. Well, it is great.
Bringing the lunch. 2:30.
Oh, yeah. So we back into the yeah, you get there on the
So if you go, basically, this is direction at the corner, so this is Euclid, where Euclid